As we begin our study of limits and finding whether limits converge or diverge and try to find the limits of a sequence, we are going to be using many different theorems. One theorem that we've been using quite often is L'Hopital's rule, but L'Hopital's rule is not always appropriate. So what can we do if we have a problem that would not involve L'Hopital's rule? We'll be discussing that today. At the end of this lesson, you will be able to find limits using limit laws, the sandwich theorem, the continuous function theorem, and limits that arise frequently. So I'm just going to go through a big list of just different limit laws that we can use to help us out. Alrighty, these limit laws that I'm just going to quickly go over, we use them just by common sense, so they're not really anything that we have to memorize because we're already doing them. I just want to point out that these actually are laws and they are legal for us to do it. The sum rule just says if we have two different sequences and they're added together, we can just find the limit. So even if I just had like 2n plus 3, you can find the limit of each one of those separately and add them together. Same thing with the difference. We could find each limit separately and subtract them. If we have two sequences that are being multiplied together, we'll just find their limits and multiply their limits together. Same thing with the quotient rule. If we have two sequences divided by each other, we can just find each of their limits separately and divide them. And then if we have a constant in front of our sequence, such as a 2 or 5, we can just find the limit and then attach a 2. And again, we use these all the time without even thinking about them, but it is legal to do those things. All right, the next thing that's called is the sandwich theorem. This is most often used with sine and cosine. It might also be used for a power that keeps switching back and forth, a sequence that keeps switching back and forth between a negative number and a positive number. And sandwich theorem, basically we're going to sandwich our sequence in between two other sequences. And if we can do that, so we'll find if we can find a sequence smaller than ours and larger than ours, and the limits of both of my outside sequences are the same thing, then by default, the one on the inside, the one that I'm looking at, will also have that same limit. So let's do an example. The limit as n approaches infinity of sine n over n, if I were doing this sequence, the first thing I would try to do is try to plug in infinity. And if I do that, sine of infinity does not exist because the sine function continues to toggle back and forth between 1 and -1. So I'm in trouble. So I can't even try to start using L'Hopital's rule. None of those other limits will really apply that were on that last page. So we get to use the sandwich theorem because if you think about the sine value, the sine is never going to be smaller than -1 and it's never going to be larger than 1. So we're going to sandwich this sequence in between two sequences. We're going to sandwich it between -1 over n, and we'll put sine of n over n in the middle, and we're going to sandwich it between. So this sequence actually is between these two. The n's are all the same on the bottom, so I'm really just looking mostly at the numerators when I sandwich it. All right, so now what I'm going to be doing is we're going to find the limit of each of our endpoints as n approaches infinity. So if we do this first one as n approaches infinity, if you just plug in infinity, you'll end up getting 0. Okay, and on this side, as we let n approach infinity, again, 1 over infinity will again be 0. And so since our two endpoints have the same limits, that means the limit of our inside will be that same thing also. So we just found that the limit as n approaches infinity of the sine of n over n is also equal to 0, and that is due to the sandwich theorem. Okay, continuous function theorem, we basically use this without thinking about it as well. This theorem allows you to treat a sequence like a continuous function, and that's a lot of times we will treat a sequence like a function so that we can use L'Hopital's rule when appropriate. We just need to make sure that the sequence is a continuous function. So we do need to make sure if I look at this that we have nothing in the denominator that's going to make this equal 0, which we don't. All right, the first thing that I'd like to look at before we actually find the limit, we're talking about sequences and them acting like functions. What does this sequence look like? So the first term I plug in 1 and I get 1/3. The second term would be 2 over 9 because I'm just plugging in 2 for the n. The third term we plug in 3 for the n and I get 3 over 27. The fourth term I'd plug in 4 for the n's and get 4 over 81. And then it keeps going. So what we're trying to find is, as I approach infinity, what number am I getting closer to? All right, and to do that, since this is a continuous function, we can go ahead and just use the rules like we're used to doing, like we did in the last chapter. So if I plug in infinity for both of these, I do end up getting infinity over infinity, and since I did get infinity over infinity, that allows us to use L'Hopital's rule. One thing when we're using L'Hopital's rule, please remember that we still want to let our reader of our paper, whoops, we'll use an N this time, we're letting the reader of our paper know that we're finding a limit, so we really do want to write that down. So if I take the derivative of the numerator, I'll get 1, and if I take the derivative of the denominator, it will be 3 to the n times 1, because the derivative of n is 1, times ln 3. Okay, and if we do that, if I plug in infinity now for my n, I will end up getting 0. So my answer is 0, and this sequence would converge. All right, we next have some limits that arise frequently. These are ones we'll use sometimes if we need to. Sometimes we'll end up with the answer anyway, but if we're stuck in a problem, some of these will just help us get unstuck. All right, the biggest thing on these problems, you'll notice I have some x's in my problem and I have n's in my problem, and that's going to get just a little bit confusing. N is my term number. So n, if we're dealing with sequences, that's really our variable in the problem. And for all of these problems, x is going to be treated like a constant. X can be any number. It can be 5, 2, 7, whatever is given in the problem. Okay, if I have this first one, the limit as n approaches infinity of the natural log of n over n, I would get 0. We could actually use L'Hopital's rule quite easily on this problem so that we didn't have to memorize that limit. The next one, the limit as n approaches infinity of the nth root of n is equal to 1. That will be a very helpful one. We'll have the limit as n approaches infinity of x to the 1 over n is also equal to 1. In this case, notice my x has to be bigger than 0, so it might say 2 to the 1 over n, 5 to the 1 over n, something like that. Okay, the next one will have the limit as n approaches infinity of x to the n will equal 0, assuming that x is less than 1, or the absolute value of x is less than 1. This is one you can probably just figure out without memorizing. We'll do an example like that to see. The next one we won't use real often, but if I had something, the limit as n approaches infinity of 1 plus any number, it could be 3 over n, 5 over n, and it's raised to the n power, this will actually equal e to the x. And then my last one, if I have the limit as n approaches infinity of x to the n over n factorial, I will always get 0 as that limit. And n factorial, just to remind you, as an example, if it said 3 factorial, that just means 3 times 2 times 1. 5 factorial means 5 times 4 times 3 times 2 times 1, just so you're familiar with that. So I've just discussed a lot of different limit laws that we can use when we're finding the limit of a sequence and to see if a sequence converges or diverges. So we'll just use these when necessary.